So today we are getting an introduction to what are called logarithmic functions. And logarithmic functions are inverses for an exponential function. So the definition is for any positive base b, where b does not equal 1 because that's not exponential, you raise 1 to any power, it's still 1, that's a linear function. Then the log base b, so that's how we're reading this right here, log base b of y equals x, if and only if, I didn't spell that wrong, that means if and only if y equals b to the x power. So again, the logarithmic function is the inverse of the exponential function. If you do the composition of a log and an exponential, they cancel each other out and you get back x, what you started with. So one other thing I want to point out here is what I call the curly law. So if you take a look at our log function, you start with the base, raise it to the x power equals y. That's exactly what we have here. The base b raised to the x power equals y. So when you're converting between log and exponential functions, I find it a lot easier to convert from log to exponential because the curly law works, but I always think about that when I'm converting the other way to check my answer. So you kind of curl around that log function. So we've got a little example here, log base 3 of 81. So in your head, what you think is 3 to what power equals 81? And the answer is 4. 3 to the 4th power equals 81. So log base 3 of 81 equals 4. And I already gave the answer. So I'll jump down to the common log. This is a log base 10, so we don't actually write the base 10. If it's log base 10, we would just write log of x. And then we assume that we know we're talking base 10. And by the way, log base 10 is the only log that your calculator will evaluate. And finally, we've got a couple properties of logs. We'll see quite a few more in our next lesson, but some of the basic ones is log base 0 of 1 is 0 because b to the 0 power is 1. And I'm looking at this, that should not be base 0. This should be base b. Log base b of 1 equals 0 because, thinking about our curly law, b to the 0 power equals 1. And our second one, log base b of b equals 1 because b to the 1st power equals b. So we're going to start with converting. We know that 3 squared equals 9, so we're going to write this in logarithmic form. So we start with log base. Now when you look at the exponential form, the base of the exponent is 3, and that remains the base of our log. 3 to what power? 2 equals 9. So log base 3 of 9 equals 2. Again, as I said, converting from log form to exponential is a bit easier for me. So we start with the base of the log raised to the, in this case, 1/2 power equals 5. Because the square root of 25 is 5. Remember those rational exponents. Next, we're going to take a look at comparing the graphs of the exponential and its inverse, the log function. So we'll take a look at a couple of values for our exponential function. 4 to the negative 2nd power is 1 over 4 squared, or 1/16. 4 to the negative 1 is 1 over 4 to the 1st, or 1/4. 4 to the 0 power is 1. 4 to the 1st is 4. And 4 squared equals 16. The inverse is log base 4 of x equals y. And remember, when we looked at inverses, you switch the x and the y. So that's what I'm going to do to make my table for my log function. I'm going to take the t-chart that I just made, the y becomes the x, and the x becomes the y. just did something wrong. I didn't switch my 4 and my 1. All right, so we have our t-charts, so we can graph each of these functions. So remember what the exponential function looks like. It starts off really close to that x-axis, and the bigger the base, the faster it grows. So at -2, I'm at 1/16. I don't know that I can even really get a point that close to the x-axis. 1 is 1/4, 0, 1, 1, 4, and then I've already got my 2/16 is going to be off the chart. And then again, that gets really, really, really close to the x-axis, and there really shouldn't be any space in there, because as far as our eyes would be able to see, we wouldn't be able to discern it. So now for my log function, 1/16 over down 2, so that would be about here, pretty much on that y-axis, over 1/4 down 1, over 1 down 0, over 4 up 1, and then of course my 16/2 is off the graph as well. So look how this is flipped across that line, y equals x. So if we were going to jot that line down, there are reflections across the line y equals x, and the asymptote flips. So for the exponential, it's the x-axis, and for the logarithmic, it's the y-axis. Video's getting a little long, but I think this page will be fairly quick, and this is our last one. So we're going to practice evaluating logs using our brains and what we know about exponents. So thinking 4 to what power equals 64, the answer is 3. 4 cubed equals 64. So log base 4 of 64 equals 3. 2 to what power equals 1, 0. Now see, we have log of 1,000. Remember, if we don't see a base, we assume that it is 10. This is the common log. So 10 to what power equals 1,000? And the answer is 3. For D, we have to think a little bit. 7 to what power equals 1/49? So looking back here real quickly, when we did 4 to the -2 power, our answer went in the denominator. So if your answer is a fraction, your exponent was negative. 7 squared is 49. To move it to the denominator, it would have been a -2. And our last one, 1/3, this one looks a little tricky as well, to what power equals 27. But think about D and E being very similar. On D, we were taking the log of a fraction. On E, we've got the base as a fraction, but it's the same principle. We need that fraction to flip. So our answer is negative, and 3 cubed is 27. So 1/3 to the -3, thinking about evaluating that, the negative exponent would mean flip what's inside the parentheses, so I would flip that to a 3, and then raise it to the 3rd power. That would give me the 27. So here are a few log functions for you to evaluate.